before the Spanish Inquisition, I would have to say I believe in the Father, the Son, and the Holy Ghost. If I was in Iran, I would have to say I believe that there is only one, there is no God but Allah, and Muhammad is his prophet. So I'm doing the scientific equivalent of that. So I'm stating what I believe. This is going to be in the first 3 slides. After that, we get to science. The first part is religion. Okay, so this is elements of my religion, that I believe that intelligence should be thought of in a biological setting. It emerged through evolution like 550 million years ago. You have the first animals which could move and they could see. So this loop between perception and action is fundamental. There's this line by Gibson: we see in order to move and we move in order to see. In more modern, we move to primates. We have the emergence of bipedalism, so the hand is free. Once the hand is free, then you can do tool building, and the development of the brain follows the development of the hand. The fossil record sort of seems to suggest that. And there's this great quote from this Greek philosopher Anaxagoras: "It is because of his being armed with hands that man is the most intelligent animal." Okay, then we get to like last, maybe Neanderthals had it in language, but that's a million years, or maybe only modern humans had it, in which case it's 100,000 years. But that's when we get language, abstract thinking, symbolic behavior. So if you think of intelligence as being over 24 hours, starting from the Cambrian explosion, language is the last 2 or 3 minutes. Okay, so that is the importance of language in this whole story, at least in my book. So you can't argue with it because this is my religion. So, okay. The other aspect of my religion is, so that was phylogeny. This is ontogeny, the life of a single individual. I really love this quote from Turing, which is, instead of trying to produce a program to stimulate the adult mind, why not rather try to produce one which simulates the child's? And Turing didn't know much about child development, actually. He just proposed this. I mean, there was some work before him, Piaget and Vygotsky and so on. But really, in the last 70 years, our colleagues in psychology have really done an amazing job, and we know so much about it. I mean, and I'll capture that with this slide, which is meant to be kind of a summary of so many findings from the people who've studied children. I mean, Allison is an example of folks. So these are multimodal, be incremental, be physical. I'll make this more concrete. And then one more statement of credo, which is in this nature versus nurture debate. I'm largely on the nurture side. So I want to have the minimal possible assumptions from nature. And currently, for me, those are the structure of rewards. I think they are sort of genetically induced, and then the curriculum of child development. So I think rewards and the curriculum, these are the only things you need to build in, and the rest can emerge from data, from learning in the. So there's a line, I think Kronecker maybe said this: God created the natural numbers, all the rest is the work of man. Now, Pietro told us that we don't even need God for the natural numbers, but I like the original quote better. Okay. So now let me just launch into it. And I think that if you want an organizing theme, I think that these insights from child development really guide me. And what I'll show you are flavor applications of these in various ways. It's not a coherent theory. I have vignettes. Coherent theories will come. A single unified model will come later. I don't have that yet. But think of it as we see through a glass darkly. Okay, so I'm going to start with this, which half of the people in this room have seen, but I think it sets up the problem, so I must start with this. Okay, take the problem of locomotion. It's like a classic problem, right? It goes back 550 million years. And we thought we had an answer to this. So people who are in the nature camp, they will say there are central pattern generators. These exist. I mean, there's no question that they exist, and they can account for gates. And in fact, the early developments in robotics were based on this concept. So you have phase-shifted oscillators, and the different legs are in different phases, and it all works out. And you can learn with very minimal amount. I mean, you build in relatively little, and you can get behavior like this. Now, this is just not true of human babies, by the way. So Karen Adolph at NYU, she has been studying real babies in real natural environments. And basically this model of gait, which may be true for mountain goats, is not true for human babies. And so the behavior, I'll show you this example, which is nicer. So this is like a kid who has just learned to walk. And let's see how she walks. Okay. So now you can annotate this. So this is, she walks to the side, to the front, back. There is no gate here. Okay, there is no systematic gate. There is no pattern generator driving the loops. Whereas pattern generators actually do exist in humans too, because evolution never throws anything away. It just adds stuff, but doesn't really throw things away. So the point is, there are multiple mechanisms. There are mechanisms which are much more learning oriented, which is what we have with humans. And so we set about in our work trying to create models of this. And so it's a learning-based scheme. And so reinforcement learning is the natural tool here. And we had talks in the morning from Sergey and Pulkit. So they've sort of they've talked about the space. The reason why we do learning in simulation is because children's bodies are very robust, and they are robust to falls. And they are soft bodies, so they can deal with like 1,000 falls and it's fine. My robot cannot deal with 1,000 falls, so I have to do this robot in simulation. So this is the reason, and this is a problem in practical terms, but we have to do this. We have to work in simulation. And it turns out that so we set about a learning approach. So just the little bit of notation here, this base policy is some neural network which is outputting an action. The action is in terms of all the joint angles, and the input is the state of the robot, which is in terms of joint angles plus the desired actions. And the interesting part here is that, so you're going to do a neural network to learn this policy. You can also think of this as a controller. As a control theorist, you can think of it as a controller. The interesting part is this Z sub t, which corresponds to the fact that you have to be able to walk in many different kinds of terrains: flat ground, sloping ground, sand, etc., etc. And it turns out that, so you need to estimate that, but you can estimate that in an outer loop. So the idea is something like this, that when I'm walking, if I apply the same forces, if I'm walking in sand, then when my foot sinks in and I try to lift it up, it will come up a small amount. And that is a signal that I'm in different conditions. So the longer history of your state action pairs gives you an opportunity to essentially figure out what is the environment which is captured in this latent variable Z. And that's what was the insight in this work. And other than that, so there is something built into the architecture, but other than that, it's a pure learning approach. Unlike sort of some of the previous work in Locomotion has always been with much more nativist in that sense. Okay, and then okay, and it works. And let me show you an example. So this is a robot learning to walk, and what you will see here is that, in fact, there is olive oil on this carpet, and then there is some plastic legs, socks on this robot. So what happens initially is that it sort of stumbles a bit. Sorry. It stumbles and then it recovers, and that's shown in the gate here. And the way it's happening is that this latent variable Z, which is some 8-dimensional variable, is capturing what kind of a terrain you are in. And it's being estimated dynamically in some loop. Now, what kind of behavior does this prove? I mean, robotics always has to be tested in the real world, and these are examples of a robot in the real world. So dealing with natural obstacles. By the way, this robot is blind. It's completely blind, and the signal is basically proprioception, all the joint angles of the body. And it works in settings like this. And now let me show you some examples of emergent behavior. I think Sergey talked about this. Why we love reinforcement learning as compared to just training with tons of data. with reinforcement learning, new behaviors can emerge that were not programmed in, because reinforcement learning is essentially solving the problem of optimal control by a search algorithm. And so here what we did was we have the robot, it's being trained to walk, it's given a target speed, 0.375 meters per second, 0.9 meters per second, 1.5 meters per second in these different cases. And different gaits emerge. So this is the gate that emerges when you say walk at 0.375 meters per second. This is the gate that emerges when you say go at 0.9 meters per second. So this is not programmed in. There is no data here of walks that are, and this is what you get when you say go at 1.5 meters per second. So reinforcement learning can find genuinely new solutions. So this is I think important. So that's why we love this. And the secret sauce here is that in the cost function, the rewards, as I said, the only two things I want to build in are rewards and curriculum, and the rest should emerge by learning. So in the rewards, there is minimize energy consumption. And minimizing energy consumption has to be a very basic evolutionary principle, right? Metabolic cost for these animals who hunt and are hunted is important. And it turns out, and this is findings from biomechanics, that in different regimes of speed, different gaits are optimal. So for humans, at low speeds, walking is optimal. At high speeds, running is optimal. And for horses, you have multiple gaits. Okay. It's basically energy and smoothness. That's it.
Smoothness over what variable?
Smoothness over the movements of the joints. So yeah.
All of them.
Yeah. Okay. And now, what's the value of perception? The value of perception is that it enables smooth locomotion. So it enables precise locomotion. So if you want to cross blind people can walk, but blind people don't want to probably walk across a river, across these stepping stones, and they'll be hesitant to cross stairs. And so we find that, so we developed a system for doing this, and following roughly the same philosophy. So you have one neural network, which is the policy, and then there are other neural networks which are capturing these aspects, the physical aspects of the environment, and like friction and so forth, but also the geometry. So now what's important here is that there is a policy which is end to end. It is not, in this case, following a separation principle, which is beloved of classical control theorists. But the classical separation principle is really valid in, I mean, those are valid theorems, but they are all in linear type of settings, and we have a nonlinear setting. So at some level, the way I want to connect all this to control theory is that we are trying to solve a problem of control, but it's a problem of adaptive control, because in this different, so control theorists have x prime equals ax plus bu, and a is this system dynamics. But in different settings, mountains, slopes, flat ground, sand, you have a different a. And that is, in their case, in the classical control, you need to have different controllers for different conditions. Here you have one neural network which is being tuned by this input of z. But let me show you the results with now we have vision, but it's onboard vision, and this is what the system can do. So this is the image that it sees on the top right, and it does not know the environment in advance. And from trial to trial, we move these objects around. So if it makes a mistake, it falls. Okay, and this robot, when it falls, we pay for it, right? Because the legs break. And I would argue that this is a capability that Boston Dynamics, which has been at it for like 30 years, they couldn't do stepping stones in this kind of stochastic variation. Pulkit talked about this as well. I think this paradigm of training in simulation and then transferring to real in locomotion has really caught on. So I think in locomotion, we have had the equivalent of the ImageNet moment, that learning approaches are better than classical approaches. Okay. So now, great. So that was mainly meant to set the mood, because now I want to get you to think about what motor control problems are. and what are the aspects of it. And now I want to give you some vignettes of how, at least for me, this inspiration from child development has led to particular designs of robotic systems which have worked out well in practice. So the first one is multimodality. And here I want to reference Andrew's talk, Andrew Zimmerman's talk. He talked about how multiple modalities give you a very natural way of supervising each other, how they are powerful. And I'll show you that in a robotics context now. So the first example is again a basic one, which, so think of rotating an object in the hand. So this is an example of a dexterous manipulation task. Okay, let's just see it. Okay. So we have this four-finger hand, which is trying to rotate an object. And this task is actually not so trivial because you can rotate about any axis. So this is the rotating about the z-axis. Okay, this one is probably easy, but you can also rotate about x-axis and y-axis. Okay, that's what you see in the top rows. And it's exactly the same policy, and it has to generalize across all these different objects. And we had a paper on this earlier which did it just blind and without tactile sensing for this rotating about the z-axis. And we tried to do that for these more complex tasks, and it failed miserably. And what we found was that for more difficult manipulation tasks, you really do need more sensing. So I think that robotics people tried, I mean, this is sort of a realization from evolution. Why perception is important. Perception is important because it provides you much more robust control. And vision and touch are very complementary. When the object is far away, only vision works. Touch has nothing to say. When the object is in the hand, then touch is all important, and because your vision is occluded. And of course, this happens in a continuous way. And so I'm going to skip the details of how we trained it. We have a camera looking at the object. We also have tactile sensing on the fingertips. And by this time, we sort of moved to using transformers. And I want to make one meta statement. So a lot of, I mean, the whole field of AI has gone through these various stages of neural networks, right? Perceptrons, convolutional nets, LSTMs, and right now it's like the transformer era. And indeed, we found that's happening in robotics as well. And one finding was that we did not any longer need to separate these two stages. I mean, there's work we have in bipedal locomotion led by Ilya, which shows this as well, that you can have the stage of estimating something about the environment and your walking policy. It can all be there as part of one big transformer with enough context. Okay, but the slide that I like is this one, which is what do you get from the use of different senses? So if I don't have any vision or touch, this is my performance. So y-axis is performance. This is my performance if I have knowledge of the ground truths. I know the exact shape of the object. And it turns out if you just have vision, you do at this intermediate level, just have touch, you do like this. And vision and touch gets you almost the same as ground truth knowledge. Performance is in simulation. So this is like how many times you can rotate without it falling, something like that. So this is cool. This is, I think, at least for this task, it is showing the value of vision and touch, and the fact that both of them working together is good. And my belief is that this is what you'll find as we study different manipulation tasks. I mean, the senses have evolved for a certain reason. Another finding, which I don't have a slides right now for this, is that you do not need the exact shape. And this connects somewhat to Tomer Ullman's talk. You do not need the exact shape. You need the affordance-like approximation of the shape. So we can actually probe into the network and find what it thinks is the shape. And it's kind of an approximation to the shape. But that's good enough, right? For manipulation, you do not need every little detail of the object. You need some kind of an approximation, and the policy discovers that as part of the learning. Okay, here's another little vignette, which is on the power of multimodality. And here what we said was we wanted to make this dog learn to walk with just vision, but we wanted to do learning in the real world using cross modality. So this is again very much in the spirit of Andrew's talk. So think of this. I'm trying to train this vision system to help the robot walk, and the difficult task is stairs and so on. And I want to do it in a self-supervised way. Okay. Now, how do I do it? It's difficult. But here's the cue. Proprioception, all the joint angles of the robot, they actually carry information about geometry, right? Because once you know all these joint angles, you can do some simple trigonometry and multiplying matrices together, and you know the height of this foot and that foot and so forth. So when the robot is at a particular location, its body knows all these depths from just the geometry of the limbs. Okay, but what do I need? I need my vision system to tell me that in advance, right? Because that's what is going to help me not fall into the river and get on the stepping stone. So that's basically what we do here. And so the proprioceptive perception has the right data, but now what we do is, okay, if you just take this signal and shift it in time, so you say 2 seconds later, you know the exact depth, and now my vision system tries to predict that in advance. So it's self-supervised by a shift in time. And again, I think this is not so far off from AZ's talk. He was doing it with vision and audio, but I'm doing it with vision and perception. And you've got your self-training signal here. And this works beautifully. Yeah, we didn't study that thoroughly, but we had like basically a constant speed. So it was like a fixed 2 seconds, but it should depend on the speed. Yeah. And there's data for humans on that, right? When they walk faster versus slower, how they look. So, so this is our robot walking. Okay. Oh, sorry. Okay. Now you'll see it walk with increasing amounts of experience. Okay. So it's basically learning in the real world. And this is day 2. and this is day 3. And it's learned in the real world from this data. And here are curves. So the success rate goes up, and the error of this prediction, cross prediction error, comes down, and it's very hunky-dory. Now you have a system, by the way, which can deal with a varying body, because it's adapting all the time. It's always being constantly calibrated. So we have an experiment here where Antonio here is going to mess with the camera of the robot. Okay, sorry, I don't know if my video is messed up or not. It probably is. But okay, the point of the demo was supposed to be that you take this camera and you rotate it by 30 degrees. I mean, it really messes it up. So initially, it just suffers. It like collapses up. But it's collecting data which is correct in the with the new camera, and then it works. So this is like there's this classic prism adaptation experiment for humans. You put a prism in front of one of the eyes, all the rays are deviated. So when I try to reach the object, I'm off. But I keep trying, and after 10 minutes, I become great. I'm perfectly normal. And now if you remove the prism, again, I'm messed up, but then I can learn to redo it. So this is the model here, and we showed that it actually works here. For upside down, yeah, that also works. I mean, in fact, the person who did it was our colleague in psychology, Stratton, in psychology, who did it around 1900 or so. And he did these experiments of learning to bike with upside down images. And he managed to do it with this, basically the same experiment. Yeah. Yeah. Okay. So, so this is multimodality. I think the moral is very clear that multimodality is great, and essentially it enables self-supervision. Modalities supervise each other. Incremental. So this is why I said that I need to bring in the curriculum, as I say, I want to allow from nature. Okay. So incremental means that you learn one task on top of another task. You have some capability and then you layer another capability on top. You do not learn tabula rasa. So, I mean, we don't learn tabula rasa. Normally, this is used as an argument for nature versus nurture. I'm saying nurture itself has multiple stages, and a previous round of nurture helps the next round of nurture. That's what I'm going to argue for. And here's an setting here. Okay, I think I'll start with this demo first. So we have our robots which can walk, and now we are training more complicated behavior. So this is chasing behavior. So this is like pursuit evasion games, which okay. But this is actually more interesting because there are times when the target sort of disappears. She manages to hide effectively. Then the robot has to look around and so forth. Then okay, let me just enjoy this for a little bit, and then I'll give you the scientific lessons here. So you probably noticed this, that it's not going to where she is; it's going to where it thinks she will be. Okay, and so again connects to so-called differential games and so forth. But here, what we did was we trained a policy, a second order policy on top of low level walking policy, and this is the pursuit evasion policy, and this is trained completely in simulation as well. Okay. And with the objective is obviously to catch up to the target, and various things emerge. So the seeking behavior emerges, chasing emerges, going to where she will be rather than where she is. All of that emerges. Okay, and beautiful views of beautiful Berkeley. With you know, okay. Another example which of this hierarchy, you have one scale, so a child has some capability and then other capabilities develop on top of these capabilities. So this is the reorientation task. So I think Pulkit had demos of reorientation, which is you have a certain matrix, certain rotation matrix which you want to apply to an object. So how do we do that? So we have these policies for rotation. They don't give you reorientation directly because you have to know when to stop. So you have to pick an axis, rotate about that axis, and then stop. And it turns out, so this second order task can itself be learned on top of this first order task. And it's much easier to learn it in this two-step way than tabula rasa. And these are like demos which show rotation about different axes. And I can assure you that this is a task which is hard even for humans. Okay, so so z-axis is easy for humans, but these are more challenging, and I should run it. But these markers are actually not used by the algorithm, but it's meant for you to, as a human, to convince yourself that it's doing the right thing. So I'll move on here. Okay. Let's go to another vignette. Social. Social means learning from others. So children learn from their parents, from their peers, etc., etc. So one example that I have here is this is work we did like ages ago, which was, suppose you have some YouTube video of somebody doing this kind of cartwheel. Can I use that to train this robot? So this is the Atlas robot of Boston Dynamics. So it's a reinforcement learning problem because it has to meet the physical criteria, constraints. It's a physics simulator. But the reward is sparse. At the end, did you succeed? And basically, it doesn't work. But if you make the reward dense, that at every moment you're trying to be like the human pose. You can't be exactly, because the human physics is not exactly the same as the physics of the robot, but it gives you a much better signal to guide. And it turns out this works. So this was in simulation, but I want to take this principle and apply it much more generally. And here we have this most recent work, which led by Ilya, who's at the back of the room, so he can answer questions in the break. So here, what we are doing is, okay, now, of course, we use transformers, and the approach is that you have lots of trajectories. Okay, let me give you some examples of those trajectories. So you have video data of humans playing tennis, but this means that there's this human walking, right? We have computer vision techniques which can 3D-fy this human and figure out the joint angles as a function of time. I can then use that and put that on my robot. So now I have a robot trajectory. So basically, I can copy humans to get trajectories for the robot. Okay, but this by itself is not going to be enough. Okay, so you need it to be robust, and Pulkit talked about this. He said you need positive examples and negative examples. So just acknowledge that. But we have these trajectories. That's one aspect, and they can come from variety of sources. Another point is that we train with transformers, and the task here is next token prediction. So the next token prediction task is what people use in language. But how to think about it conceptually? So the way I want to think about it is that uh, the space of humanoids walking is high dimensional, 30, 40 dimensional, which is problematic for always RL type algorithms, right? Because the higher the dimensionality of space, the bigger the search space. But from these trajectories, you are essentially implicitly learning a lower dimensional space. I mean, that's what self-supervised learning does in language. And now your search is in this lower dimensional space, so it's more efficient. And this can be quantified in terms of hours of training time that you need for the robot to learn how to behave. So, and then, of course, there are some details here, which is that from the sensory motor trajectory, you don't have access to, like from these visual trajectories, you don't have access to the internal action commands of the human. So it's partial data, but that's fine. You can have some way, some technique for dealing with that. Okay, so let's look at the results. So this is, okay, so let's see. So this is the humanoid in San Francisco. Okay, and I mean the contrast here is, I mean, this is our work from like a very pitifully small group at Berkeley, and we are at this time competing with all these companies with like zillions of resources and zillions of researchers. Okay, so but sometimes there is a value to having the right idea. Okay. Okay, so now I think, so this is, and now I have results that Ilya sent me half an hour before this meeting. Okay, because I was nagging him to show him his latest results. So now we have the latest results. Okay, so because, I mean, the impressive setting is more difficult terrain. Okay, so perhaps we don't have that full degree of robustness as for the quadruped. So biped is harder than quadruped, right? Obviously. But okay, I actually haven't really seen this video properly, so it's as much of a surprise to you as me. Okay, so these are hiking trails in Berkeley, in the Tilden Park. So I don't know what this slope is. I don't know if but it's, so anyway, there's certainly variation in terrain. I think you will see later on more, sort of San Francisco street slopes. And it's one policy, right?
It has vision.
No, it's blind. I mean, blind people can walk. I mean, we'll need vision for crossing rivers, okay? But, huh? Because there's somebody behind giving the direction vector. So the obstacle avoidance is being solved by a human. Yeah. So so there's a. Okay, so that's slope. Let me see if there is something. I hope there's some San Francisco street coming up. Okay. So Ilya, what are the slopes of these streets? What's the slopes you have tried?
So this is equivalent to the steepest street in San Francisco.
Okay.
The one that's known as the steepest, but it's an equivalent.
Okay. So anyway, so this one is interesting because this is, I think the paradigm here is a more general paradigm, which is what does data help you with and what does reinforcement learning help you with? Reinforcement learning is a fancy way of saying search, trial and error. The data helps get you to the right low dimensional manifold. The search is needed for finding the right policy. Okay. I think that the two can work together. And you can, in fact, imagine bootstrapping and alternating these steps and so on. Then, does this paradigm work for manipulation as well? But long time ago, I was a student of, when I was a kid, I was a student of Donald Knuth, who used to have this line in his class, and which was, if something works once, it is a hack. If it works twice, it is a technique. So I need to show it worked twice. Okay, so this is the task of manipulating objects, and this is where robotics is going to be spending the next decades, right? So so the hope is, now we have big data. There's 156 million hours of video on YouTube. So if I can make every hand into 3D, and if I can make every object into 3D, then I have 3D trajectories, and then I can transfer them to the robot. And so what do you need to achieve that? So how much time do I have? Like 5 minutes? Okay, 5-ish is good. Okay. So I need to 3Dify the hand, and I need to 3Dify the object. So what can we do? So for 3Difying the hand, we have this paper where is George here, George Pavlikos. So he's the lead on this. We basically have solved the problem of how to 3Dify hands, but let's show you the video. So frame by frame, it's processing the image and converting the hands to 3D. It's a parametric model called Mano. Okay, let me move it along the way. So these are all being analyzed frame by frame without temporal smoothing. And this is, people in computer vision know how hard a problem this is, because there's self-occlusion and not enough resolution, etc., etc. Yeah, but now you see interaction with objects and so on. And yeah. Okay. So we can do 3Difying of hands. Can we 3Dify objects? So this is another work, and let me show you the results. So the key idea here is that reconstructing an object in the hand is actually very hard. The reason is because most of it is occluded. You don't have feature points, structure for motion will not work, blah, blah, blah. But the hand provides an anchor for the rest of the object, right? Because if there's an object which is touching two fingers of the hand, then you kind of know the distance between the fingers, so you therefore know the distance, the size of that dimension of the object, and so forth. So we have this generic 3D reconstruction system that we developed earlier, but now we use it in the context of this hand object data, where the hand is lifted first to 3D, and then the object is being reconstructed in that context. And okay, usual obligatory numbers, but these are boring. But let me show you this. So the aim is that this can just work on arbitrary YouTube videos. Okay. So this is a reconstruction of the hand and the object. And the 3Dness is being shown by looking at it from different angles. And in results from like yesterday night, which I don't have a video of, this works at the video scale, where you can use temporal smoothness and use like the Viterbi algorithm for doing globally optimal reconstruction. And basically, you can get trajectories out of it. So this machinery can be thrown on 156 million hours of YouTube to get data of human hands manipulating objects. Here's another demo. Okay, let's see. Yeah, so these are, I wish, if I had more time, I would show you the video of this evolving over time. So it's 4D really. So this is 3D in one frame, but I can actually do this in 4D. Okay, well then what's the next step? Now we have to solve the problem of using these to train a robot to pick up and manipulate objects. And that is stuff we finished at 4 a.m. I think one of the people who finished at 4 a.m. is here. And these guys did not deliver the video, the final video to me. I wanted it. I asked them at 10 a.m., which was a mistake because they were probably sleeping. But yeah, so the idea is like this. You see humans manipulating an object like this, and then we get our robot to do the same. And this works now. So this is, and again, the ideas are actually very similar to what I showed earlier for walking with Ilya's work. You have you alternate these steps of data. So use the data of human trajectories, and with that you're essentially finding this low dimensional manifold, because otherwise you have way too many degrees of freedom. And then you are doing reinforcement learning in that space. So you have positive and negative examples, and then you transfer from the simulator to the real world. And here are some numbers which probably are not accurate for the latest model, but there's pre-training via next token prediction, and then fine-tuning with reinforcement learning. So there's data and RL. And real world, okay, I should delete, this is an old slide, real world results as of yesterday. All right. And thank you very much.
Questions?
So does sim to real work now? Can you just also keep learning and that's it?
Sim to real, I mean, it's never not, it doesn't work. It's hard, but we can make it work with some, blood, sweat, toil, and tears. So I believe in sim to real. I know it is a challenge, and but I don't know of any other way to deal with this negative example problem. You have positive examples and negative examples. When you for RL, you need negative examples as well, and those are much easier to produce in simulation, because in the real world my robot will get broken after 1,000 trials. Now, what if you have got the right setup, then you can fine tune finally in the real world, but now it will need a very, very low sample complexity, and then it'll be fine. Yeah.
So I'm up next, so I'll start setting up, but
Okay.
we have time for more questions.
Okay. Okay. Hi.
So you mentioned that if the robot falls down, it breaks, and babies are squishier. And also, I noticed, I don't work with robots, but it's like really noticeable that all their knees kind of go the opposite way. Whatever body is like optimal for these robots seems different from animal bodies to some extent. So I was partly curious, like, just why do the knees go back that way? And also, if you have thoughts on like how the material properties of robots might help solve some.
Yeah. So I believe in the 3 Bs. So the 3 Bs are brains, body, and behavior, and these are coupled. And but I'm not a mechanical engineer, so I work with the robots I am given, and I believe that the robots today are quite suboptimal. And the reason why they are is because in the old days, without the development of the learning infrastructure, the way robots were designed was that classical control theory tools would work, which means that they had to have analytical models. But this is no longer true. Right now, we can use learning tools, so we have much more flexibility. So my belief is that over the next few years, we'll see different bodies, better hands, better humanoids, and coupled with the learning paradigm, we are going to see big changes. So I'm not happy with those humanoid bodies. I'm not happy with those hands. They're clearly very inferior to humans.
Thanks.
Let's do one more question and then I'll take over.
Yeah, exactly.
By curriculum, you mean learning this task and learning the other task. Don't organize it in terms of easy to hard.
Well, yeah, I don't know what the easy, what is easy, what is hard, but by curriculum I do mean task A, learn task A, then learn task B, then task C. And I am imposing that structure myself. I'm not letting, so ideally you should have that emerge from learning as well, but I'm cheating. So this is where I'm putting in prior knowledge. And roughly it corresponds to easy and hard in some ways too. But that's like us human putting an attribute. But so far we have been able to find what seems very natural, so to speak. Do A, then do B. So we learn walking before we learn chasing, for example. But I think of this as like a generic paradigm for motor development between the age of 0 to 5. The child acquires a great deal of expertise, and it's with skills which are layered on top of other skills, and then on top of other skills and so on.
Okay, let's thank Jitendra.